All right, so previously we just kind of solved for IA, and then we went ahead and used this table here to show us that obviously it's saying that we can just find the IA, or the line current for a Y to Y connection, by taking the voltage from A to the neutral divided by the load impedance, or in our case, there's both a line impedance and a load impedance, but because they're in series, it doesn't make any difference to us, right? What I mean by line impedance is that, so on a real like transmission system, you might have like a three-phase generator here, and then obviously you've got your three phases coming out to some kind of a tower, right? And then these signals get transmitted to some kind of maybe it's your house or something, and this might be your phase A, B, and C, and or this is some industrial place that needs three phases, right? And so inside of the factory or wherever this thing is at, that's where your three-phase load is going to be something that looks like this, where this is the neutral, right? And so then the neutral would theoretically be connected back, but because there is no current flowing in it, you don't need that cable. But the important piece here is that this cabling that's carrying the power down the distribution of the power down these transmission lines have impedance themselves. They're not perfect conductors, so they might have a little bit of resistance, a little bit of capacitance, etc. And so, and inductance for sure. But it's important to note that that's what's happening in a problem like this. You might wonder, like, what practically, why is there an impedance here and an impedance here? Well, this impedance here is actually meant to model your load. So this is this would be 10 plus J8. And a balanced load it just means that all of the loads are the same impedance. So 10 plus J8, 10 plus J8, and then the one in the middle is the same as well. And then these lines, since they're all the same, they all have the same impedance too, ideally. So they're saying that this line has an impedance 5 minus J2. This line has an impedance 5 minus J2, etc. But because for phase A, the 5 minus J2 is in series with the 10 plus J8, we just added them, right? We can just add them up and get 15 plus J6. And that's the same for phase B, and that's the same for phase C. So really for all three phases, you know, we look at it. I mean, we just have the same equivalent impedance, which we found here. We found it to be 16.155, angle 21.8. And so I'm going to go to the next slide now with some of this work that we did. Let's just grab it all and just show kind of the proof that, you know, we used the table to compute our currents, but we don't need to do that. We could also just note that in order to find IB and IC, all I'm really doing is I'm saying IX, whatever that value is it's going to be VX neutral divided by the impedance, which in our case we found to be 6.155, angle 21.8 degrees, right? That's our impedance for one of our lines plus our load, and they're all the same. So if we want, we can call that ZY, like the book called it, right? In the table, they called that ZY right here. We don't have to call it that. We could just call it Z, but yeah, let me just write that out. We'll just call it Z. Let's call it ZLL, Z line plus load or something. And that's going to be equal to VXN divided by, so for us it's 16.155, angle 21.8 ohms. And so what am I meaning by this X? Well, I mean that if I want to find IB, all I need to do is put VBN here divided by ZLL. And if I want to find IC, all I need to put is VCN divided by ZLL, right? That makes sense. And so for IB, it's going to be 110 angle minus 120 divided by 16.155 angle 21.8. And so now you can see why the magnitude stays the same, right? It's 110 divided by 16.155 again. So I'm going to get the same magnitude. But instead of 0 minus 21.8, it's minus 120 minus 21.8. And that's why I get that IB is 6.81 minus 141.8, right? Angle minus 141.8 amps. And that's exactly what we got by just looking at the table. It's because all we're doing is we're replacing this phase shift of 0 with the phase shift of minus 120 when we go to the B phase, right? And so for IC, it would be very similar. It'd be 110 angle plus 120 divided by 16 point, I don't know why I'm having such a hard time writing this, 155 angle 21.8. And so we have to subtract the 21.8 from the plus 120, and that's where we'd get our IC is equal to 6.81 angle 98.2 degrees amps. All right, so clearly, I just want to make it clear that what I was doing here was I was basically just solving what we already solved for in this problem, which was the line currents IC, IB. We already found IA, and I think that was pretty straightforward, but just showing that we used the table on this slide to find out what IB and IC were, but here I wanted to show where that comes from. And obviously we talked about the difference between what the line impedance is, which is literally the impedance of the transmission lines, and the load impedance is the impedance of the thing that we're actually trying to send power to, okay? So maybe I should just label this like generator, and then these are transmission lines, right? And then this is my load. All right, so I'm gonna go ahead and end this video. That's example 12.2 from the book, just finding the line currents in a simple Y to Y system. It's obviously not too bad. I think it's pretty straightforward. Maybe these circuits do look a little scary, but once you break them down, they're quite simple. Stuff that we should have no problem with up to this point in this class. So I'm gonna go ahead and end this video, and in the next video, we're gonna go ahead and solve the next example problem, which uses a different three-phase configuration here. One of the loads or one of the source configurations will be something different. All right, so I'm gonna end this video right here.